Hey guys, Clellan coming at you again, this time with finding equations of exponential functions. Building on what we learned yesterday about exponentials, now we have some data, we have some info, and we're gonna use that to determine an equation to model it. It's exactly what our scientific experts right now are doing to analyze this coronavirus, so very timely, very cool. Here's the general form of any exponential function. So we have an output equals a times b to the x. So it's really as simple as this. Analyze what's happening and figure out what the growth rate is. This function here is tripling. Times 3, times 3, times 3. This goes back to geometric sequences back in Algebra 1. So this times 3, that's the b value. Every time, whatever your multiplier is, in Algebra 1, we call it a common ratio. The common ratio from each y to the next is going to be the b value. It's the base of our exponential growth rate. A is always going to be this value here where x equals 0. That's our y-intercept. So we just plug them in to the general form and we've got the equation. We can verify this by creating a scatter plot. I'll show you how to do that in just a moment, but we can also do it algebraically. Let's just plug in and make sure that our model works for every data point. Remember, anything to the 0 power is 1. So far, so good. Anything to the first power is itself. Three to the second power is 9. Everything's looking good. And yeah, our equation or our model is perfect. Okay. Let's see how to do that with a scatter plot. I found one just by Googling exponential regression calculator. So go ahead and do that. This is the first result that came up. We're looking for an AB exponential regression, not an E exponential regression. That's a different kind of growth rate. Here's one from Casio that's pretty great. You just clear out these values, you put in your data. And then you hit execute. And this is what we're really interested in here, these A and B values. We get the graph and a lot of advanced statistical information, but that's what we really want to confirm, that our A and B values are correct, and they sure are. So moving on, example 31, we got two value pairs, an X and a Y. We could create a chart, or we could do this algebraically. I'm going to show you both ways. Here's the data we know. We don't know these, but we do know this. So all we got to do is really just guess and check until we find the constant multiplier, common ratio. And I've done this ahead of time, so I can tell you that it's 5. So if you multiply 8 times 5, you get 40. And then you multiply by 5 again, and you get 200. And then you multiply by 5 one more time, you're going to get 1,000. So we basically have everything we need, because remember, this is our A value and this is our B value. And we can literally just put them together now. And spoiler alert, our final answer is going to be, let's see. I was just checking the directions to see if they wanted us in function notation, but it doesn't say so. So that would be good to go. I prefer this look, but that's a matter of preference. Here's how you can get that algebraically. What do we know? Here's a piece of information we know, that f of 3 is 1,000. Well, don't forget that those are x and y values. And we know that a is 8 from up above. So we have all 3 out of 4 of our variables so far. We can just plug them into the general form. And we have 1,000 equals 8 times b to the third power. We can divide by 8 to get at that b value. And we have 125 equals b to the third. Well, if that's the case, then that means that b is the cube root of 125, which is 5. And voila, we have the info we're looking for to create our equation. Final answer. Boom, moving on. Let's see. So here's a scenario where we just have 2 points and we don't have that wonderful x equals 0 value, that y-intercept. So we kind of have to work around that. So what we're going to do is substitute both of these points in, create a simple little system of equations that's pretty quick and easy to solve. For b, plug that in and get a. So let's start with the coordinates they gave us. Now I kind of like them in reverse order, and you'll see why in a minute. So I'm going to put this one first, and then this one second. And I'm going to plug those in to the general form again. And so what that gives us is a times b to the fifth. Come on. Equals 121.5, and a times b to the second equals 36. Now, if I were to divide those, I could cancel off those a's, and that's what this next part says. So it's going to look a little weird at first, but I'm going to line them up like this and divide these two expressions. Now, if I divide the left sides by each other, I'm going to have to divide the right sides as well. So that cancels out our a's. Anything divided by itself equals 1. And don't forget, this, I believe, was rule 2. If you go back earlier in the notes to our rules, we're going to subtract these exponents. We're going to get b to the third again, this time equals 3.375. That means that b equals the cube root of 3.375, which means that b equals 1.5. That's step C, so I'm done there. I can just move on and solve for A. So now you can use either point. I'm going to choose the smaller one, 2 comma 36. Remember, this is an x, this is a y, and we now know b. So again, we know 3 out of the 4 values. We can use that information to find the fourth. A times 1.5, this case to the second. 15 to the second is 225, so 1.5 is 2.25 equals 36, and then we're just going to divide by 2.25 to solve for A. So A comes out to 16, and we can just put all that together to state the final equation. Sorry, A is 16 times 1.5 to the x power. An important note, if they want function notation, if it says create a function, you have to write f of x equals. But this one doesn't. So we're good to go with either of these equations. Okay. Moving on. Page 16. This is going to be very similar, especially part B through the end. Part AS is about average rate of change. The only difference is now it's just a word problem. It's about a bacterial colony. So again, very timely, growing at an exponential rate. It's known that after 4 hours, hours are generally our x variable, and the amount of bacteria depends on that. So we have two XY pairs in disguise again. And I like to put them in reverse order again, and you'll start to see why in a moment. I generally do the bigger pair first. Remember to label. People really, if people make mistakes, it comes from not labeling, I found. We're in a rush and we don't pay attention to the little details. Plugging in. By the way, I kind of just launched right into this, but average rate of change is just slope for things that aren't straight lines. That's why we call it average rate of change instead of just rate of change. You spend so much time in like elementary and middle school learning about just linear relationships that we don't spend enough time talking about curved things having an average rate of change, just what's happening at the beginning and the end, forgetting about the middle. Anyways, this comes out to 91 over 5, which is 18.2. But this question says interpret the average rate of change in the context of this problem. The minute it says that, we have to talk about the story. This is 18.2 bacterium per hour. That's my final answer for part A. Moving on, we need to determine equation again, y equals a times b to the x for this new scenario. So this is literally the same as what we just did. Again, copy your coordinates over or your xy values and then plug them in to the general form of a of an exponential. You'll notice that I'm going to start to do it more like this. A times b to the x equals y. I just find it a little bit more practical to have the y value on the right. So we got a times b to the ninth equals 189. And we got a times b to the fourth equals 98. Dividing these to cancel out the a's is going to give us b to the fifth power equals 1.92851. Yep, that's a mess, but real life is messy. Get used to it. Just kidding, this sucks, hang in there. But that means that b is the cube root, the fifth root of this 1.928571 number. So then b is 1.14 approximately again. Just noting they asked us to round to the nearest hundredth. And then I can use that to solve for A and have everything I need to create the equation. Remember, you can solve for A using any point on the curve. They gave us 2. I'll choose the smaller one again. So I'll choose this one, 4, 98. We're going to plug in then y equals a times b to the x. So we got 98 equals, actually I'd rather write a times 1.14 for b to the fourth equals 98. Let me draw a line there. I got to raise 1.14 to the fourth power. I got 1.689 roughly times a equals 98, and then let's just divide by 1.689 to get a equals approximately again 58.02249er. Actually, another 9. But again, we're supposed to round to the nearest hundredth. So my final answer is going to be y equals 58.02 for A times 1.14 to the x power. Double checking that I don't have to put this in models y as a function of the number of hours x. So y and x should be my variables in this scenario. Very important to check for that in a real practical situation. And I'm out of time. Miss you guys.